Hey guys, this is Quantum Trio. I am AS Janani from Grade 8 Royal Concord International School.
This is Anika Ashwin from Grade 8 Royal Concord International School.
This is Lakshya B. Raghavendra from Grade 8 Royal Concord International School.
Astroalgae Synthesizer. Project Overview. This project aims to provide a temporary solution to the pressing environmental stewardship challenges we face today, while we work together to restore and remedy the damage we have caused to our planet. In In addition to this, the initiative is specially designed to support our efforts in space exploration projects, drawing inspiration from Dr. Ivan's innovative liquid tree, which utilizes microalgae to replicate the process of photosynthesis. We have adapted and expanded upon this concept. Our enhanced version of this technology is intended to play a crucial role in ensuring human survival for research purposes in space. Issues faced by liquid oxygen stored in spacecraft. Contact with liquid oxygen can prove to be extremely hazardous as it may cause skin and eye discomfort and burns and in some cases frostbites as well. Inhaling pure oxygen at high pressure can lead to adverse effects such as nausea, dizziness, muscle spasms, vision disturbances, seizures, and even loss of consciousness. It may also cause genetic mutations by inducing oxidative stress and damaging cellular DNA. Prolonged inhalation of pure oxygen can irritate the lungs, and extended exposure may result in fluid accumulation in the lungs, pulmonary edema, a serious medical condition characterized by severe shortness of breath. These are the components. Solution. What is overall concept of the solution? We have developed a comprehensive solution to address the issue outlined. This system provides oxygen in its natural, gaseous, and safe state. The apparatus consists of 152 liters of water and 1.4 kg of chlorella vulgaris. How does the system enhance growth and reduce water requirements? To enhance the growth and reduce the water requirement, photobioreactors are employed and are held in place by supporting frames. The addition of these reactors cause a drastic change in the water requirement, creating a positive impact on the design. What nutrients are added and how? Certain salts are infused in the water in specific quantities to support the growth of the algae. Sodium nitrates, potassium phosphate, calcium chloride, and magnesium sulfate, and ferric citrate are the major nutrients to be included in each photobioreactor. These would be infused in the form of nutrient tablets in the photobioreactor. Centralized inlet unit is positioned at the top center of the glass apparatus, shared by both photobioreactors, and this unit consists of a tablet storage hopper connected to an electrical linear actuator which dispenses one tablet at a time. A Y-shaped diverted chute controlled by a servo motor directs each tablet into the appropriate PBR inlet through airtight tubing. A neon chip automates live intervals and facilitates efficient release of these capsules. Multiplication of algae can be controlled by limiting nitrogen and phosphorus.
Now, how does the lighting system support photosynthesis? The implementation of the LED chips of solistic LED light bulbs would be a beneficial upgrade to the astroalgae synthesizer. These chips, when affixed to a flexible printed circuit board, mimics the original spectrum of the sun's rays, and when aligned to the wavelength to about 400 nanometer to 700 nanometer, it contributes to the process of photosynthesis. Now, the FCPBS are connected directly to the spacecraft's main power bus with the help of coils, the transmitting coil and a receiving coil, along with the DC circuit board, which receives power from a local power tap in the spacecraft to facilitate more regulated voltage supply. A lithium ion polymer battery would be positioned close to the receiving coil outside the photobioreactor. The power received by the receiving coil facilitates efficient charging of this battery. The battery would be connected to a battery management service which prevents overcharging of the battery. With thermal management, this battery would be suitable for functioning by enduring extreme temperatures and radiation. Now, how are gases monitored and controlled? Gas sensors are placed at the top right and left corners of the setup to regulate oxygen as well as carbon dioxide levels. A Firestring O2 optical luminescence based oxygen sensor at the top left detects oxygen levels and controls the opening and closing of the sliding glass doors. Carbon dioxide is monitored using a sensor sunrise non dispersive infrared sensor. Both the sensors measure and display oxygen production and CO2 consumption rates on an onboard LED screen while transmitting the data to Earth for research. Programming is done in C++ via a Leon microcontroller, which also serves as the interface between the sensors and the space via databus. The Leon processor is embedded within the onboard flight computer, requiring no direct external connection. Now, what is the structure of the apparatus and how exactly does it function? The apparatus is enclosed in a glass container with permeable PDMS membranes bonded via plasma treatment and sliding glass doors operated by an electric linear actuator controlled by the Leon chip. Now, the photobioreactors or the PBRs are lined with the PDMS membranes to prevent water evaporation. Oxygen sensors trigger the glass doors to open, releasing oxygen and allowing carbon dioxide intake, maintaining a continuous gas exchange cycle. Temperature regulators keep the system between 25 to 30 degrees Celsius, ideal for algae growth as well as photosynthesis. Now, two such apparatuses are installed in the spacecraft, each containing two PBRs with 260 grams of Chlorella vulgaris in 38 liters of water. They operate alternately in 12-hour cycles, ensuring continuous oxygen production and balanced respiration periods for the algae. How is dead algal biomass processed into protein supplement capsules? Now, a key feature of this project is the conversion of dead algal biomass into 1 gram protein supplement capsules. Approximately 78 grams of dead biomass is collected every 6 days and transferred via space grade silicone tubing into a food processing unit connected to the main apparatus. Dead algae, being denser, settle at the bottom of the photobioreactor, where an LKG5001PV laser displacement sensor measures the sediment thickness. When it exceeds 1 centimeter, the Leon chip triggers a 12V solenoid valve controlled through an IRL Z44N transistor on a nearby driver board to release the settled biomass into the tubing. A peristaltic pump then pushes the biomass into the food processing unit for capsule production.
Let us now dive further and figure out how the food processing unit functions. The food processing unit, or the FPU, consists of 8 chambers, namely the intake, ultrasonic disruptor, dehydration, UV sterilization, empty capsule storage, forming, storage, and dispensing chambers. The biomass slurry first enters the intake chamber via silicone tubing, where a MacBotics MB7389 ultrasonic level sensor, which is linked to the Leon chip, monitors the fill levels. At approximately 80% capacity, a peristaltic pump and solenoid valve transfer the slurry to the ultrasonic disruptor chamber, which contains a mini homogenizer emitting 20 to 40 kHz waves. Cavitation caused by these waves breaks algal cell walls, releasing proteins, lipids, and vitamins. The slurry then moves to the dehydration chamber, maintained at 35 to 40 degrees Celsius using a VETENG NTC thermistor and Cole-Palmer PID controller. A stainless steel vacuum line removes vapor, and a dryer master 2220 moisture sensor triggers transfer when moisture is approximately equal to or greater than 5%. The UV sterilization chamber lined with 265 nanometers UVC LED strips disinfects the biomass. An Apogee SU 100 UV dosimeter halts UV exposure at 30 to 40 millijoules per centimeter square and activates actuators and solenoids to send material to the forming chamber. The empty capsule storage chamber uses a Leon-controlled stepper motor to feed the capsules into the forming chamber, where a piezoelectric microdispenser fills each capsule. A Rudra miniature load cell stops dispensing once 1 gram is reached, and a micropiston seals and pushes the capsule into the storage chamber. Finally, a stepper motor in the dispensing chamber releases 1 capsule at a time when the user presses a button beside the food processing unit, automatically opening the sliding door for retrieval. How is the power supplied and communication managed within the system? A wireless power system using XKT 412 coils draws energy from the spacecraft's power tap to operate the sealed astroalgae synthesizer. Now, this receiver coil feeds an LM2596 converter that supplies regulated power to the ESP32 microcontroller, driver boards, and all sensors, pumps, and actuators. The IRL Z44N transistors on the driver boards manage high current components safely. An NRF24L01 Plus transceiver enables wireless control and data exchange with the spacecraft's main system. This is a reference diagram of our oxygen production unit. We are now having a look at the reference diagram of our food processing unit. Thank you.
Thank you.